talk about tomorrow. But for now, we're just going to do these two. So I should warn you, today is going to be pretty mathy. It's going to be pretty math oriented. We're going to look at a lot of math stuff. So might as well dive in, I guess. So we'll start with deposit profit over here. Okay. So basically, we're talking about a bank account situation. We've deposited some amount of dollars. That's going to be one of the parameters that they're giving us. So this one here, deposit. And we're basically depositing it at a given rate, an interest rate. And we want to find out how long is it going to take for the balance to pass this threshold. And I guess, let's see, we're making a few assumptions here. So it doesn't specifically mention it, but this is going to be compounded annually. So if you know anything about like compound interest versus simple interest or anything like that, there are different compounding styles. So it could be compounded like monthly, weekly, continuously. There are lots of different ways, but in this case, we're just looking at the simplest case, which is that it's being compounded annually. Okay, so that's nice. I mean, that's like sort of one fewer thing to worry about for us. So let's see. Basically, the idea, they want to know like how many years is it going to take for it to reach or exceed the threshold. So in this case, 170. So they give us an example here. They say you invest $100 at a rate of 20% per annum. And we want to know how long is it going to take for that to reach or exceed $170. And they sort of give us these numbers over here. So in case you're wondering about this, because like we're talking about it growing by 20%. So this is kind of like the difference between simple interest and compound interest, is that with simple interest, we would basically take the interest on the principal amount, so the deposit in this case. So it's say 20% of 100, that's $20. So with simple interest, year 0 would be 100, year 1 would be 120. Then year 2 would just be 140, year 3 would be 160. We would just be adding $20 each time. So why are these numbers different? Well, basically, as we go from each one to the next one, we're taking 20% of what exists and adding that on to what we already have. So basically, 20% of 100, yeah, that's $20, like we said. But then 20% of 120 is not just going to be $20, it's going to be $24. So we'll add that on, we'll get 144, and then 20% of that is a more complicated number, which when we add to 144 gives us $172.80. And this challenge may have been written by someone European, since they're using a comma instead of dot for the decimal point there. Okay, so how are we going to do this one? Well, we could start with some kind of loop, right? So we'd say something like let years, or I guess I'll say year, right? Because it's going to change. We'll say the year starts at 0, and it's the thing that we're ultimately going to be returning at the end, return year. Okay, great. So basically what we want to do is do a loop, which is essentially going to execute this, it's going to run through this, do the same sort of thing. So it's going to say for let, I guess we'll say amount. So this is going to be sort of like the current amount that's in the bank account or whatever kind of investment it is. And we'll say it's going to start with deposit. I mean, at the very beginning, it is going to be equal to deposit. And we want to continue this as long as amount is less than threshold. Is my autocomplete off? Let me take a look. Oh, yes, it is. Let's get both of those in here. Okay, great. All right, and I need a third part to this, but I'm just going to leave it blank for now. Okay, so, and in fact, like we could close that up, make it a nice little winky face in there. All right, so, oh, thanks, Levita Briss. How late is it anyway? It's about 6:30 here in Ontario. Okay, so let's see. Amount is going to be, well, basically what we're going to be doing is we're going to be taking 20% of it. So we'll do amount times rate. right? So taking that 20%, multiplying it by what the amount already has, and then we're going to add to that whatever the amount was already. And just out of curiosity, I want to do some console logs here. That's going to give us the amount in here. So yeah, let's run that. Let's see what ends up getting logged. Okay, so first of all, nothing happened here with the year. I mean, I think the idea is that I probably should have incremented the year, maybe a year plus plus. That might have been a good idea for this over here. And basically what's happening with the amount, we've got 2100. Seems a bit big, doesn't it? This one, we started with 100. The rate was 1. It was 200 right off the bat. I mean, it feels like these things are growing a bit too fast. And it makes sense because the rate is being given in the form of a percentage, right? Like 20%. But if you multiply something by 20, it gets way bigger. We want to actually represent it as a decimal. So 20%, if we kind of dissect the word percent, it means like per 100 out of 100 sort of thing. So basically what we're going to do is instead of just rate, we're going to rate divided by 100. So that's something you got to keep in mind when we're talking about these kinds of compound interest questions. Wow, look at that. Okay, so passing all the tests. It's good. And if we look at the numbers in here, they're the numbers we expect. So we get the 120, we get the 144, we get the 172.8. We don't see the 100 in there, and it's because the console log is happening after the amount has already been reassigned. Okay, so that was not too bad. I'm going to get rid of the console log. I'm going to do one other thing here just to make this a little more, I guess, a little more efficient in terms of how it looks anyway. I'm going to do a plus equal. So instead of saying amount is on the value of whatever it was plus this additional amount, we're saying amount plus equals 20% of what it was. Or you know, whatever rate was. Okay, so we'll run that, and now keep in mind this is no longer going to be a percentage, it's just a decimal. And there we go. Okay, so that's looking pretty good. But the question is, will it pass all the hidden tests? Let's try. So we're going to try submitting this. We'll see where it goes. Yeah, okay, so that's not too bad. It passed all the tests. I guess, you know, at this point we can move on, but I don't want to do that quite yet. I feel like we haven't fully explored this one. Okay, so what could be done differently? Well, what I really want to do is I want to talk about kind of a formula we could develop for these kinds of compound interest questions. So we're going to do sort of, I guess we can do an example. So we'll say over here, I'll just do a little t-table, and it's going to look horrible. Sorry about that. And we'll have the year over here, and we'll have the amount over here. Now, normally I would ask, if I was working with a student, I would ask, you know, would you prefer to use kind of like a general example? Do you want to use a specific example? So if anyone has a preference, let me know in the chat. But for now, I guess just to sort of get started, I'll use sort of a specific example. So I'll go over to the description. I'll use this one. So deposit is 100. We're depositing $100. The rate of growth is going to be 20%, and the threshold we're looking for is 170. That's not going to be all that relevant for this one, but we do want to say that it's going to be. Maybe I'll write the information over here. So deposit equals 100, and we'll say rate equals 20. Okay, there we go. So year. We'll start with year 0, and the amount in year 0 is just going to be whatever we deposited, so it's just going to be 100. And that's kind of why, if you look at the algorithm over here, we started by letting amount be equal to deposit. So far the two are kind of consistent with each other. All right, great. So what's going to happen after a year? Well, we're going to get 20% of this, right? So basically, we're going to do 100 times 20%, which would be 20 divided by 100. I could either write it at like, 20 divided by 100, but for a few reasons, mainly the amount of pen strokes involved in that, I think it would just be easier to just write it as 0.2 So as long as everyone's okay with that, I'll just write it as 0.2. Maybe I'll make a note over here referring to this. So 20 divided by 100 equals 0.2. And even maybe to make it even more clear, after the 20, I'll put a little percent symbol there. Okay, I'm really bad at drawing those. Anyway, okay, so notice after year 1, we have 100 times 0.2. There's just going to be 20, but that's not all we have. That's just the new stuff that we have. So we have the existing 100, but we're adding on to that 100 times 0.2, which, yeah, is going to be 120. But I'm not so much interested in that. I'm more interested in like what this looks like, where it comes from. So what I'm going to do next, and this might seem kind of weird, kind of backwards, but I'm going to factor out 100. Both of these things have 100 in them. So I'm going to factor out the 100. So this is common factoring. I'm going to put the 100 out in front, and then the idea is that, well, we'll just divide each of these parts here by 100. Let me underline them. So that divided by 100 and this divided by 100. Okay, so what's going to be left over when we do those divisions? Well, 100 divided by 100 is 1, and then 100 times 0.2 divided by 100, well, it's just going to get rid of the 100, so we're just going to be left with 0.2. Okay. Cool. And yeah, as it turns out, and I'll just switch colors for this, that is going to be equal to 120. Okay, great. So we found out the amount at the end of year 1, and it looks like it's consistent with what we have over here. So looks good. Let's continue. So we'll say year 2. Now with year 2, we're going to have the same sort of setup here. We're going to have the 120 that we already had, but then in addition to that, we're going to add on 120 times 0.2. Okay, now again, we could multiply these out, we'd get 24, but that's not the part I'm interested in. What I'm interested in is, let's factor out the 120 here, and we're going to be left with 1 plus 0.2 again. Now, by the way, I should mention, like, in case you're wondering about what's going on here with this common factoring business, because I know this is kind of something I had an issue with for probably a longer time than I'm comfortable admitting. But anyway, the idea is that it's the reverse of the distributive property. So you may remember, like, if we've got a number being multiplied by a binomial, like, two things in a bracket, basically what we can do is distribute this number into each of these. So if we wanted to actually multiply this out, it would be the same as 120 times 1 plus 120 times 0.2. Now what I've done here is basically the exact opposite of that, because 120 times 1 is 120. 120 times 0.2 is 120 times 0.2. So basically the idea is we can do the reverse of this distributive property, and that's basically what common factoring is. So just in case you're unsure about that. Anyway, if anyone has any questions about this, for sure, let me know. I realize we're getting pretty mathy this time. Okay, so basically the idea now is that it's 120 times 1 plus 0.2. But where did the 120 come from? Well, it was just 100 times 1 plus 0.2. So let's replace it with that, because it's equal to that, right? 120 is the same as 100 times 1 plus 0.2. So I'm going to write that out. I'm going to say 100 times 1 plus 0.2. Let's round that 0 out a little more. Great. And that's just the 120, right? The remaining part is still going to be part of it. 1 plus 0.2. Great. So basically, we've just taken the 120 and we've replaced it with what it's equal to. Everything else is staying the same. Okay. So then what's interesting about this is basically this and this are the same thing, right? We're just multiplying this thing by itself. Now, you've probably seen a situation like that before, where we multiply a number by itself, and there's a more efficient way of writing it. Instead of writing it out twice, a number multiplied by that same number, we can just say it's going to be that number squared. There we go. Okay, that number squared. So maybe we're kind of noticing a pattern with this. I mean, like with, here, let's write this out. This is going to be 144 now. So with the previous one, it was, okay, we started at 100. Then we did 100 times 1 plus 0.2. Then the next one was 100 times 1 plus 0.2 to the power of 2. Okay, maybe we'll do like one more of these and we'll see if the pattern we're noticing holds up or not, but I guess I just need more space, so I'll scroll down a little bit here. Okay, so we're going to do the same thing as what we were doing before. We're going to say this is going to be year 3, and we're going to have 144, that was the amount that already existed, plus 144 times 0.2, because it's 20%. So it's basically the interest that we're getting. So this is the original amount over here, this is the interest over here. Okay, great. So then 144 plus 144 times 0.2, well, that's the one that's going to get a bit awkward to calculate. So instead of multiplying that out, I'm going to factor out the 144, and that's going to leave us with 1 plus 0.2, which is becoming a very familiar number. Okay, so now I want to replace 144 with what it's equal to, which was 100 times 1 plus 0.2 to the power of 2, and of course that was just the 144 part of it, so still left over is this stuff at the end here, 1 plus 0.2. And now we've got, okay, I'm just going to start calling this 1.2 because that's what it's going to be. 1 plus 0.2 is 1.2. So we've got 1.2, it's being squared, and then we're multiplying it by 1.2 again. So in total, we're multiplying 3 instances of 1.2 together. So we can just say that's 1.2 cubed. All right, now I kind of alluded to this a minute ago that there's maybe a bit of a pattern happening here, and I want to point out what that pattern is. So, okay, first of all, check this out. We're looking at, well, actually, maybe I should have started at the bottom. Yeah, that's probably better. Okay, so in year 3, the exponent was 3. In year 2, the exponent was 2. And if we scroll up, we'll notice in year 1, there was no exponent, which means the implication is that the exponent was a 1, right? There's only one copy of it. Then you might say, well, in year 0, it didn't have an exponent of 0. And that's a good point. But as we've seen in the past, any non-zero number to the power of 0 is going to give us 1. So it is the same. Even if we multiplied it by 1.2 to the power of 0, it would still just be 100. Okay, so let's take stock of all this. Let's put it all together, right? We'll try to come up with a master formula here, which I'm going to write in green, and I'll make it a bit bigger than some of the other stuff here. So what do we have? We have 100, which was our deposit. So I'll say D for deposit, and then it's being multiplied by 1 plus, yes, patterns, exactly, Toching. Okay, 1 plus 0.2. 0.2 was the rate, right? So I'll say R, but keep in mind, we did divide it by 100 in order to get the decimal form of it as opposed to the percentage form. So it'll be R over 100. And then this thing right here is the year. I'm just going to call it, I guess, N for now. Number of years, I guess. And then we'll just say that the amount, so we'll use A for that, the amount is going to be equal to this. Okay, great. So that's our formula. We'll use that. This is going to serve us well, I think, for going back to the problem. We'll try to implement this. But I don't know if I emphasize it enough. Let's just do another one of these. Just because we really want to catch the reader's attention with this thing, so. Okay, good. That's, yeah, there we go. That's better. Okay, so our amount is going to be equal to our deposit times 1 plus the rate divided by 100, all to the power of n. Okay, where n is like the year in this case. Okay, so should we bring it back? Let's bring it back. Let's go over here and we'll say, hey, this was our first attempt at this thing. It was a nice algorithm. Worked out pretty well, right? But we're going to archive and we're going to try something different now. So what's going to be the same as what we had? Well, we're still going to have let year, and we're still going to return year at the end. Except now we're going to say for let amount be assigned the value of deposit. I guess we'll just make that the same, and we'll say amount is less than threshold, and year plus plus. And now all we have to say is amount is going to be equal to deposit multiplied by 1 plus the rate divided by 100, and all of that is being raised to the power of year. Okay, and let me just tighten that up a bit. There we go. Let's run that. Let's see if that works. Oh, wow. 0 out of 3. Well, that's pretty discouraging. I mean, I really felt like we were on fire over here. And now, okay, it's taken a bit of the wind out of my sails, but let's see what the problem is. Okay, so we're saying it's 4 years when it should be 3. We're saying it's 2 years when it should be 1. We're saying it's 7 years when it should be 6. You know, I'm noticing a bit of a pattern here. Once again, I think if we were to do something like this, maybe everything would work out for us. Yeah, everything's working out for us. But I have to say, I don't like this. I don't like the idea of subtracting 1 because I can't convince the reader that that's a good idea. You know, if someone's looking at this, they might look at this and say, okay, but why subtract 1 from the year? Like, there's nothing here that would indicate that. And I want this to be clear to the reader. So let's think about why that's happening. Well, basically, if we use this first example as an example, then, yeah, exactly, error by 1. So what we could say is we're starting with year 0, right? Our amount is going to be deposit. Now, when it first runs this, it's actually keeping the year 0. So remember, 0, like raising it to the power of 0 is just going to make it 1. So it's still just going to be 100. So we started it as 100, and then we're reassigning it to be 100. Which is kind of inaccurate. It's kind of not what we want. So then after that, we're incrementing the year by 1. And then we're checking if the amount is less than the threshold still. And if it is, we're running it again. Okay, so the problem here is that we're incrementing the year after we reassign the amount, when really we should be doing it before. Okay, so I'm going to get rid of this here. And I'm just going to put the year plus plus right here. So as we've seen in the past, it's fine to leave part of a for loop blank. Not a problem. You're allowed to do that. Okay, so let's run this. There we go. I like that better because, I mean, subtracting 1 from the year, it just feels a bit sloppy to me, I guess is the best way for me to describe that. I like this a bit better. Okay, but could it be slicker? Well, let's find out. I mean, I've seen some people do stuff like this before where they kind of combine it, you know, or they put the plus plus inside this assignment operation. So while we're assigning this new value to the amount, we're also increasing the value of year. So would it work if we do that? Well, actually, no. We're kind of back to the same issue we had before. We're off by 1. Okay, so that's no good. But there is a solution to this. See, the problem here is that it's calculating the amount with year as it understood year to be previously. And then after it completes that, then it's incrementing 1 onto year. And then the next time it runs, year will be 1 greater. We want that incrementing, the plus plus, we want it to happen before. Like we want it to first increment year, then do the calculation. So we don't want the plus plus happening after we get year. We want to do the plus plus and then get year. Which is exactly what we're going to do. We're literally going to put the plus plus in front of year. And I know that seems like kind of a silly thing maybe if you're used to seeing the plus plus after, but as it turns out that works. That's actually something you can do. Now, I do have to say, I mentioned this is kind of a mathier stream, mathier broadcast this time, but if I saw one of my students writing 2 multiplication symbols followed by 2 addition symbols, I would think, oh my God, that is nowhere near a well-formed expression. But, you know, thankfully, this is JavaScript. We're not just talking about algebra here. So that's kind of cool. You know, it's a little more slick. We're putting it all in one thing here. And like, you know, this is a situation where we could just put this on one line, but I hate that. I don't like the way it's all ragged. It goes on to the next line. No, that's no good. That's no good. We'll keep it like that. Does it pass all the tests, like even the hidden ones? Let's find out. So suspenseful. I really hope it passes. Okay, great. Whew. Had me sweating there. All right, so that's nicer. I like that a little better, but I'll tell you what I don't like about it. What I don't like about it is that we're doing this calculation more than once. The whole point of developing this formula here is that we can jump directly to whatever year we want. Like, for example, let me point this out. Okay, this thing right here, that's our amount, right? Let's say right off the bat, let's say we just wanted to return that, except instead of plus year, let's say we'll just make it year 3. Okay, we'll just say, what value do you have in the 3rd year? How much will you have? And we should expect for this first example that we're getting something like a 172.8. And look, we're getting the 172.8. And importantly, we didn't have to do any of this stuff. We didn't have to loop through, you know, like, I mean, it's not like it would make a difference because that stuff was under the return. So it wouldn't ever, like it would never be run if it's after a return statement, so it's irrelevant. But still, I just wanted to show like this is all we need to jump directly to one of these values. And so it feels like, to be honest, it kind of hurts me a little bit to be repeating this calculation, which is specifically designed to not have to repeat yourself, right? To not have to use a loop. So if this was a problem where they were specifically saying, like instead of threshold, if they gave us the number of years, like if they said, okay, your deposit is 100, your rate's 20, and we want to know what's the value when the year is, I don't know, 5, something like that, right? Then we could just use this formula once and that'd be it. But the problem is that they're not telling us the year. They're not giving us this value. They're not giving us n. They're giving us a. So that's actually kind of an interesting fact, because even though we don't have the value of n over here, we do have the value of a. Since we have the value of a, maybe we can use that. So I'm going to rewrite the formula over here. I'm going to say a amount is going to be equal to deposit times 1 plus rate divided by 100 to the power of n. Now the issue here is we're trying to solve for n in the problem here, right? I mean, that's the part that's missing. What is the year? It's not, we know what we want the amount to be. We just need to know what year makes that happen. Okay, so what we're trying to solve for is this right here. We want to solve for n. So let's do that. We're not going to use calculus for it. We actually don't need calculus. What we need is logarithms. So this is actually a good piece of advice for anyone doing math. I mean, if you're ever trying to solve for something that's inside of an exponent, if you ever want to solve for an exponent, so like one of these, you know, superscripts above here, if you're trying to solve for an exponent, then we're probably going to use logarithms. Okay, so that's a pro tip. All right. But we're not going to do the logarithms yet. The first thing we want to do is we want to divide out this deposit value here. So I'm going to divide the right side by d, and of course, whatever we do on one side, we must do to the other side. So we're going to divide this side by d as well. So we're going to get a divided by d is going to be equal to 1 plus r divided by 100 to the power of n. Okay, and now this part here is where we're going to use the logarithms. There are actually 2 ways to do this. We could put it into logarithmic form. So, you know, we could do something like this and say the base is this. The base is 1 plus r divided by 100. So we do like log and then base 1 plus r divided by 100. And the argument for that would be a divided by d. That's the power, it's what it's equal to. And the exponent, the missing part, is n. So this gives us an expression for n. The problem is the base here. So we actually don't have, like in JavaScript, you remember we've used stuff like we've done math.log, and we've also done like math.log10 or log2, which are newer ECMAScript 6 things that were introduced more recently. But that's just because 2 and 10 are very common bases that we'll want to use. If we don't put any of them, like if we don't put a custom base, if we just say like math.log, well, it's going to use the base of E, Euler's number, 2.718 approximately, which maybe we'll get into at another point in time, but it's about 2.718. It's a mathematical constant similar to pi. Okay, so since we don't have this base, we're going to do something a little different here. There is technically something called a change of base formula that we could use on this, but it's going to give us the same result as if we do something else down here. And the other thing we're going to do, the different way we're going to do it, is, in my opinion, going to be better. Okay, so we'll do log of both sides now. So I'm going to say log of this equals log of all this. And I guess I might as well just kind of erase this stuff over here. I don't want that, interfering with our actual legitimate solution here. Okay, so on the left, we're still just going to have log of a divided by d. And by the way, you might be wondering, like, you just took the log of both sides. What was the base on that logarithm? And the short answer is it doesn't matter. Any base is fine. Okay, no, that was not horizontal. The slightly longer answer is, well, technically it's going to be log base e because that's going to be the default that JavaScript uses. But it could be anything. We could make it log 10 or whatever. It's just, might as well just make it log, I guess. Here's a property of logarithms. If you're taking the log of something where the argument has an exponent on it, okay? So if you're taking log of something that has an exponent on it, you can take that exponent and multiply it by the logarithm. You can just pop it out in front. And that's what we're going to do now. So we're going to say that this is n times log of 1 plus r divided by 100. Okay, and now if I want to solve for n, all I have to do is divide both sides by that. So divide both sides by log of 1 plus r over 100 and divide this side by log of 1 plus r 100, and there we go. Okay, so our next line is just going to be, and I'm going to switch sides for this, hopefully that's okay. I'm going to say n equals, I'll try to write this in big, so log of a divided by d, and we're going to divide that by log of 1 plus r over 100. Great. Okay, now look at this. We have n. We have isolated n. The thing that we were looking for from the beginning, we have now isolated. Okay, great. And we have a closed form expression to get this. Let's make that a bit thicker, I guess. Okay, yay. All right, we got it. So there we go. N is going to be assigned the value of log of a divided by d, or amount divided by deposit. And in fact, what are we going to do for amount? Well, I guess we'll use threshold because that's the thing we're looking for. So we'll do log of threshold divided by deposit, and then we'll divide that by log of 1 plus rate divided by 100. That's the plan. Let's do it. So we're going over here. We're going to archive our previous solution as we've done in the past. And one more space there. Okay, there we go. So is everyone ready? Should we try this? Okay, let's get started. So we're going to do return math.log of threshold divided by deposit. Okay, so that was the first part, math.log of threshold divided by deposit, and then the bottom was math.log of 1 plus rate divided by 100. So let's do that, divide by math.log of 1 plus rate divided by 100. Let's try returning that. Let's see what we get from that. I mean, that should give us our number, right? Oh, okay. So notice over here, we were looking for a threshold of 170. We were basically using this equation to ask when will the amount, with what year, in what year will the amount be exactly 170? Thing is, the amount is never going to be exactly 170. It's going to be pretty close to 170 at year 3. And technically, it would hit 170 slightly before year 3. It'd be like 2.9. But again, that's assuming it's not compounded annually, but we don't need to get into those kinds of complications. The main thing is that basically, oh, these were fine. Oh, okay. These ones were right on, I guess. But basically, the idea is we just want to round it up to the next whole year, right? Because it's not going to happen in between year 2 and 3. It's going to happen in the next year. So we're going to do something that we've seen before. It's similar to floor. It's called ceil for ceiling. And we're going to take the ceiling of this value. In other words, we're going to take that value and round it up to the nearest one. Let's do that, and we'll see what happens here. I'm sweating buckets. Okay, there we go. Awesome. So let's clean this up a little bit and we'll try submitting it. Let's see if this passes all the hidden tests too. Hopefully it does. Whew. Okay. Very nice. There we go. So that passed all the tests. There were only 6 tests, so maybe there's some edge cases we're not considering here, but I think we're probably fine. I mean, look, we're being consistent with the mathematical formula here, so it's probably fine. All right, great. So let's take a step back, see where we came from here. They say a journey of 1,000 kilometers begins with a single step, and I think in programming, in math, in a lot of skills, you're just taking one step at a time, right? You take a step, keep taking a step. You just keep moving on. And eventually you look back and you realize how far you've come. It's nice to reflect on that sometimes. So, okay, great. On that note, let's see. There's just one more thing to talk about here, which is which one's best? Who wore it best? So I'm looking at this bottom one here and I'm thinking, I probably like this one the least. But now that I think about it, maybe I like this one the least, because remember what I was saying about this one, how like this is a formula we shouldn't be using more than once, and yet we are using it more than once. And also, like, we're going through a loop that's just as big as the one down here, and like it seems like this calculation is a little less complicated than this one. I actually did I forget the user's name, but there is a guy on codefights who did a JS perf, and he pointed out that this operation here, the exponentiation operation, is actually slower than just doing multiplication. Okay, so let's see. Yeah, I mean, look, in case it wasn't obvious, I think this one's best. It's big O of 1, right? Like this couldn't be more efficient. Well, in terms of time complexity, right? Because like if it turned out that our threshold was really, really big, like if instead of 170, if it was like 170 billion, then it could take a really, really, really long time for the loop to actually get there, especially if it was this one, doing exponentiation at each step. Whereas this, it wouldn't care if you give it 170 billion. I mean, as long as it's not as long as it's not too big for a JavaScript number to understand what it is, as long as it's within the range of what a JavaScript number can be, then this is going to be fine. It's just going to do one calculation. It's not going to go through any loops or anything like that. So this is big O of 1. Whereas this would be big O of something else. Like often we'd say something like a big O of n. The thing is, it's not really easy to tie down what n would represent in this case, because it's exponential growth after all, right? So like threshold isn't going to be just like year isn't going to be some sort of a factor or multiple of threshold or like some, anyway, it's a little more complicated, I guess. But anyway, the point is big O of 1 is going to be better. So, don't worry about these other guys. And yeah, that's the other thing, Toaching. When I say that exponentiation is slower than multiplication, I mean like marginally, like not significantly slower at all. I'd have to dig up the JS perf to look at that. So yeah, maybe next time, I guess. I don't have it on hand right now. So I guess, okay, we'll wrap up with this one for now. I don't have any questions, comments, concerns. No? Okay. Well, I'm not sure. Okay, good question. Is this true in all programming cases? I'm not sure. Like, all I know is JavaScript. I wouldn't be able to tell you, like, for C++ or other languages. I'm assuming there are sort of, like, performance measuring tools that are available, but I'm actually not too familiar with a lot of those. Like this whole JS perf thing it's a bit new to me, to be honest. So I might not be the best guy to ask about that, but at any rate, in JavaScript, yeah, that's the case. That exponentiation is apparently a little bit slower, and it's new too, right? Like this is an ECMAScript 6 thing. Like it didn't exist in vanilla JS. Anyway, the point is, yeah, we'll move on from there. Did I submit? I think I submitted, but just to be sure, I'm not sure if it got the big O of one thing up there. So, okay. 5011 is the solution to click if you want to know what JS the game did. Okay, and I guess we'll move on from here. So where are we at now?